Hello, my name is Yudibeth Sixto-López, postdoctoral researcher in the Department of Pharmaceutical Chemistry and Organic in the Faculty of Pharmacy of the University of Granada. I'm going to talk to you about my poster research, which is entitled Development of HDAC6 Inhibitor Assisted by Molecular Dynamic Simulation. First of all, I would like to talk to you about histone deacetylase protein, which are a family of proteins that catalyze the removal of acetyl groups from lysine on histone and non-histone proteins. They regulate the gene transcription and many other facets in the cell. Currently, has been described 18 isoforms, which are grouped into 4 classes. The class 1, 2, and 4 are zinc-dependent. We are particularly interested in HDAC6 because of its unique structural features and substrate specificity. It contains 2 catalytic domains, is mainly located in the cytoplasm, and it has non-histone substrate. It has been widely explored as molecular target for treating neurodegenerative disorders such as Alzheimer's, Parkinson, and Huntington disease because it participates in the degradation of aggregated proteins, oxidative stress, and mitochondrial and axonal transport. Therefore, the objective of this research was design, synthesize, and evaluate biologically hydroxamic acids as HDAC6 inhibitor with neuroprotective effects in a model of Parkinson's disease. As part of our approach, we combine computational and experimental techniques. We design 500 molecules, and we evaluate the ADMER profile following the Lipinski rules of 5 using 2 servers, Oscillator Property Explorer and Mole Inspiration servers. Further, we evaluate the binding affinity of the compounds by HDAC6 using the ensemble docking approach, which combines the power of molecular dynamic simulation and molecular docking. This strategy allows us to score and select the better molecules that were further synthesized following a solid phase scheme of synthesis. The molecules were also chemically characterized and evaluated in an in vitro neuroprotective model, which employs neuroblastoma cell lines and rotenone as neurotoxin. Through this approach, we design the molecules as shown in the table, and then we synthesize 7 molecules. These 7 molecules were evaluated in the neuroprotective model and lead us to the obtention of the FH27 compound, which shows an activity of 13 micromolar. Further, we evaluate the stability of the complex HDAC6 with FH27 compound by molecular dynamic simulation. As suggested by the RMSD, RG, and RMSF parameters, we observed that the molecule was able to establish an unstable complex with the protein. In addition, we have also determined that the compound form an energetically favorable complex with the enzyme, showing binding free of energy of minus 11 kilocalories per mole, which is similar to that shown by tricostatin, which is reported HDAC6 inhibitor. We also determined that this compound was able to reach the catalytic site of the enzyme by inserting in the catalytic tunnel, and it interacts with the zinc, which is the cofactor, by the hydroxamic acid group, and also form hydrogen bonds and interact with residues with residues by hydrophobic interactions. This protocol led us to the obtention of FH27, a lead compound with promissory neuroprotective activity on in vitro model, and we also obtained that it may act through HDAC inhibition and interact. We determined that it may interact by hydrophobic interaction with residues located in the catalytic site and the surface.